Welcome to The Explainer. Today, we're diving straight into one of the absolute most pressing challenges in the entire world of artificial intelligence right now, which is making AI accurate, useful, and above all else, secure. Now, we all know large language models, or LLMs, are incredibly powerful. But if you've ever actually tried to use one for serious, fact-based work using your own private enterprise data, you've probably hit a very specific, incredibly frustrating wall. So today, we're going to look under the hood at the exact technologies that are tearing that wall down.
To really understand the frustration we're talking about with LLMs, listen to how a recent academic paper from the International Journal of Creative Research Thoughts perfectly hits the nail on the head. They wrote, "Large language models can write fluently, but they cannot tell you what is actually in your PDF. They hallucinate, confabulate, and confidently miss the point. And man, that is the core issue right there. An AI can write a stunning poem for you, but if you ask it to summarize a highly confidential quarterly earnings report that it hasn't been trained on, it'll either refuse to answer entirely, or worse, it'll just make things up with absolute confidence."
So that brings us to the million-dollar question, right? How do we fix AI hallucinations without exposing our proprietary, private data to the public internet? How do we get the incredible fluency of an LLM, but grounded in the factual reality of our own internal documents? Well, to answer that, we're going to break down two critical pieces of technology. Vector databases, specifically looking at how enterprise systems like Oracle Database 23 AI handle things, and a framework known as Retrieval Augmented Generation, or RAG for short.
Section 1. Vectors. Coordinates of meaning.
Okay, so to actually get text into a database in a way that an AI can understand and use, we rely on what's called an embedding model. This is a machine learning construct built to take raw data, mostly text, but it works for images too, and transform it into numerical vector representations. So, models like BERT or Sentence Transformer are essentially acting as translators, converting our messy human language into a clean mathematical format.
Now, this is where it gets really cool. Think of these as coordinates. When we embed a word like cat, we aren't just assigning it a random ID number. We're placing it into a high-dimensional space. It's kind of like a GPS coordinate, but instead of just latitude and longitude, imagine having 512 dimensions, or even 768. And in this vast mathematical space, proximity reflects similarity. Because of that, the vector for cat is going to be mapped super closely to the vector for dog, but miles away from the vector for car. It literally maps semantic meaning.
Managing these massive multi-dimensional lists of coordinates takes some serious precision. In enterprise environments, like Oracle Database 23 AI, strict typing is enforced to make sure these complex systems don't just crash and burn. They use specific metadata utilities, like the vector dimension count function. This checks the exact number of dimensions in a vector value, meaning your 512-dimension vector doesn't accidentally get scrambled with a different format. It prevents errors before they even happen.
Section 2. Speed versus accuracy. Now that our data is translated into these meaning-rich coordinates, we run into the ultimate trade-off in vector search: speed versus accuracy. If you need to find the closest matching sentence to whatever you're querying, you really have two options. You can run an exact similarity search, which scans every single vector in the entire database. It guarantees 100% accuracy, but if you're dealing with billions of vectors, it's painfully slow. The alternative is approximate similarity search, often called ANN. This approach uses clever indexes to probe way fewer vectors. You trade just a tiny fraction of exactness for a massive, massive boost in speed.
To actually pull off these blazing fast searches, enterprise databases use some pretty sophisticated indexing. Oracle 23 AI, for example, relies on indexes like HNSW, which stands for Hierarchical Navigable Small World, as well as IVF, or Inverted File. When you query the database using the vector distance function, these indexes rapidly narrow down the nearest matches. You can even fine-tune the whole thing during index creation using parameters like EF construction. That lets you directly control the number of candidate vectors the system looks at, letting developers perfectly dial in that balance of performance and precision.
But how do we literally ask the database to do this? Well, if your task is to find the closest matching sentences across thousands of books, the absolute optimal SQL structure is a nested query with an order by clause. You've got an inner query computing the cosine distances between your question and the stored vectors, and then an outer query that sorts those scores and limits the results to, say, the top 5 matches. It is an incredibly efficient way to rank your data by similarity.
Section 3. Securing the data locally.
Finding semantic matches quickly is fantastic, But speed means absolutely nothing if we're leaking company secrets, right? And this brings us to a literal game changer, local embedding. Oracle allows you to run local ONX embedding models directly inside the database itself. This is huge for enhanced security because it means your highly confidential reports are converted into those multidimensional vectors without ever touching the outside world. You completely avoid relying on external APIs, which makes ensuring strict data privacy compliance, like GDPR, a whole lot easier.
Because think about the alternative for a second. If you don't use local models, you have to send your private data out to some third-party cloud service just to embed it. That external call could easily leak context. It's a massive data egress risk that can totally undermine your entire company's trust in AI applications. Keeping the model locked down inside the secure database environment is absolutely crucial for enterprise use.
Section 4. The RAG pipeline. Now we get to tie all these database mechanics together into a real-world architecture, straight from the researchers in the IGCRT paper. First, they parse the uploaded PDFs using a tool called PyPDF. Then, they chunk that data into 1,000-character overlapping blocks so the AI doesn't get totally overwhelmed. Next, those chunks are embedded using a 768-dimension local nomic model via Llama and safely stored in Chroma DB. Finally, when a user asks a question, the system retrieves the top 5 most relevant chunks and passes them right as context to a local Mistral 7B language model to generate the final answer.
What really takes this pipeline from a clunky search tool to a seamless, user-friendly experience is the addition of conversational memory using LangChain. Because think about it. Without memory, if you ask, what is its revenue, the AI has literally no idea what its refers to. But by persisting the session history, this specific RAG pipeline successfully resolved 93% of pronoun reference follow-up questions, compared to just 33% without it. It makes it feel like a natural multi-turn dialogue.
Section 5. Real-world RAG results.
All right, the numbers here are absolutely staggering. The researchers tested the systems across 50 highly complex queries. A plain, unassisted Mistral LLM hallucinated, meaning it straight up made things up, a massive 42% of the time. Using traditional keyword search, known as BM25, dropped that down to 18%. But by grounding the AI in semantic local document vectors using the full RAG system, the hallucination rate completely plummeted, down to just 7%.
On top of that, the researchers measured the setup using the RAGAS faithfulness metric. This basically measures how tightly the AI's generated answer aligns with the actual context it was provided. This pipeline achieved a remarkable 0.91 out of 1.0. That proves definitively that retrieval-augmented prompting reliably forces the model to actually stick to the facts found in your documents.
In this next part, this might be the absolute best part for building enterprise trust. When users ask questions about topics that were clearly not in the provided PDFs, the system didn't just guess. Instead of confidently lying to you, the explicitly instructed RAG system successfully learned to just say, "I don't know," or politely refuse the prompt, in 94% of cases. That is exactly the kind of predictable, safe behavior you want from a corporate AI assistant.
So, let's bring it all together. We've seen exactly how embedding models map, meaning how sophisticated database indexes like HNSWs search them instantly, and how local pipelines keep every single piece of data strictly private. So, if we can drop AI hallucinations to just 7% while guaranteeing zero data leakage using these grounded, local vector techniques, what is stopping you from grounding your own enterprise AI systems tomorrow? I really hope this explainer has given you the foundational knowledge you need to start answering that question for yourself. Keep learning, keep building, and we'll see you on the next explainer.